Welcome to the next lecture, my dear students. So in the previous lecture we are discussing about the alkalinity introduction. So how this alkalinity comes in water. So generally there are many compounds that can create alkalinity to water, but majority alkalinity is caused because of these three, because these are the major compounds, major negatively charged compounds which are present in the water. And what is meant by alkalinity? So alkalinity is nothing but the capacity to neutralize the acid or to neutralize the H plus ion concentration. So that is nothing but alkalinity. So this is a capacity to neutralize hydrogen ions. So these are three major compounds which causes alkalinity. And let us learn a little more about alkalinity. Generally, so whenever any organic matter, so how these ions are coming into water, I already told you in the previous lecture. So whatever the organic matter which we use, whatever be the organic matter, if you look at the water supply and wastewater collection system, so water supply we start from the source and the wastewater we collect from the community. Okay, so water supply we start from the source and we end at community, because the water supply ends at community and wastewater begins at community, again it ends at source. That means whatever the impurity which we are getting is being dumped into the source only. So whatever the impurity means what? Organic matter. So all the organic matter whichever we are getting, we are directly dumping it into the source. So because of this organic matter decomposition and all, so these whatever the compounds, so and the carbon dioxide is the outcome. So the carbon dioxide will come out of these reactions, and this carbon dioxide will react with hot water. So this carbon dioxide, so CO2, it reacts with water. So because CO2 is the byproduct of decomposition of organic matter, so this will form a weak acid, that is H2CO3. It forms a weak acid, that is H2CO3, and this H2CO3, as I told you, this is a weak acid. It disintegrates into H2CO3. Again it forms CO3 2 minus. So it's a reversible reaction. So likewise these carbonates are coming out. Okay, and this H plus reaction again meets OH minus or some other compound, and it gets neutralized. But this one presents like an ion which causes the alkalinity. Again, if this CO3 2 minus reacts with H plus, then it forms HCO3 minus. These are all very weak reactions. All of them are weak reactions only. All of them are weak reactions, are reversible reactions also. So that is why these things will form. Again, if this CO3 2 minus reacts with HCO3 minus, again this HCO3 minus reacts with H2O. So this one will form H2CO3 plus OH minus. This is very weak reactions. These are all very weak reactions. So likewise, generally this OH minus, HCO3 and CO3 2 minus will form in water. These things will come in water. Okay, so everything it is starting from the CO2 evolution from the organic matter. So that is why the carbonates, bicarbonates and caustic alkalinity is predominant in water. Now how to determine this alkalinity? Generally we determine the alkalinity using titration technique. Generally we determine the alkalinity using titrometric procedure. So using some kind of indicators. Now here we will use generally methyl orange and phenolphthalein. These are the indicators we use for alkalinity also. These are the indicators we use for alkalinity also. Here, if you want to find alkalinity, if you want to find alkalinity, it is defined as, so the alkalinity in mg per liter as CaCO3. As CaCO3, I told you already, we generally determine any concentration in terms of CaCO3 because to establish a uniformity, we generally define it for CaCO3. We define it for CaCO3. Generally here, concentration of any compound X in terms of Y. Okay, concentration of any compound, concentration of X in mg per liter, in Y in mg per liter. So concentration of X in Y, for example here the X is, let the X is CO3 2 minus. I want this concentration in Y, that means in terms of CaCO3. Then how to find that? Which is equal to concentration of X in mg per liter, okay, multiplied with equivalent weight of Y by equivalent weight of X. Equivalent weight of X. That means if you know the concentration of CO3 2 minus, and if you know the equivalent weight of CaCO3, and if you know the equivalent weight of CO3 2 minus, then we can easily find the concentration or alkalinity simply. Alkalinity is caused because of these three and majorly these two. This is minimum. I will tell you why it is minimum. But these two are the major reasons for alkalinity. So here CO3 2 minus concentration in mg per liter into equivalent weight of Y, that means equivalent weight of CO3 2 minus. What is the equivalent weight of CO3 2 minus? Equivalent weight of CO3 2 minus. So this is 12 plus 48, 50. 12 plus 48, that is 60. 60 upon 2 is the valency. 60 is the weight of the compound and 2 is the valency, right? So 2 is the valency. Now that equivalent weight is 60 by 2, that is 30. Similarly, what is the equivalent weight of HCO3 minus? See here, this was 60 plus hydrogen is added now, that is 61 is the weight of the compound. 61 is the weight of the compound and the valency is 1 only. Here the valency is 2, but here the valency is 1, that means it is 61. It is 61. So here equivalent weight of Y, so equivalent weight of CaCO3, equivalent weight of CaCO3, it is 100. CaCO3 molecular weight is 100, Ca is 40, this is 12, this is already, this is 60, CO3 is 60, 60 plus calcium's molecular weight is 40. So that means 60 plus 40, that is 100, but the valency, calcium exists as Ca2 plus, carbonate exists as CO3 2 minus. So the valency is 2 here also. That means this is also 50, the equivalent weight is 50. So alkalinity is caused majorly due to these two only. So CO3 2 minus concentration, if I find using titration technique, CO3 2 minus concentration if I determine using titration technique, then this thing I will get from titration. And I know the equivalent weight of Y, that is 50, because here the equivalent weight of CaCO3 we need to take, because I am writing it in terms of CaCO3. This is Y. Okay. Now 50 is the equivalent weight of CaCO3 and equivalent weight of X. X means what? This is X. So this is 60 by 2, that is 30. This is 30. Plus HCO3 minus, again equivalent weight of Y is 50 only. by equivalent weight of X. X means what? This is X, that is 61. So total alkalinity means we take only major, we neglect the minor. So we tell this as total alkalinity. I am repeating again and again. Alkalinity is caused by all the negatively charged particles which is having a capability of neutralizing hydrogen ion. But taking all the compounds into consideration makes the equation very complex. So that is why we neglect the minor compounds. We only consider the major compounds in drinking water or raw water. So major compounds in raw water at a pH of 6 to 8 range. Generally, the fresh water or raw water will have a pH range of, in general also it is ranging from 6 to 8. So that is why, so only these two compounds are predominant. To make our equation simpler, analysis simpler, we only consider the alkalinity causing of CO3 2 minus and HCO3 minus. And we take it in terms of CaCO3 because the molecular weight of CaCO3 is 100, so that our calculations will become simpler. That is why we take any compounds, not only alkalinity, hardness, pH, whatever it may be, we can take any concentration in terms of CaCO3 to make our equations simpler and calculations simpler. That's it. So this is the formula for the total alkalinity. So this is the formula for total alkalinity. Very, very important formula. Very. Total alkalinity in mg per liter as CaCO3 is equal to CO3 2 minus concentration in mg per liter from titration multiplied with 50 is the equivalent weight of CaCO3 by 30 is the equivalent weight of CO3 2 minus plus HCO3 minus concentration into 50 is the equivalent weight of CaCO3, 61 is the equivalent weight of HCO3 minus. So this is the formula for total alkalinity. Now, so these two, CO3 2 minus, HCO3 minus concentrations we need from titration. So now let us go to titration technique, how to find the concentrations of CO3 minus, HCO3 minus, CO3 2 minus, HCO3 minus using titration technique. Okay, see now, here we need to understand a graphical procedure. See, we are doing a titration now. So in this titration, we are allowing the acid. So generally we use H2SO4 acid. So here while doing the titration, the titrant is H2SO4. Titrant is strong acid. We need to use strong acid to determine alkalinity. We need to use strong base like NaOH to determine the acidity. So if you want to determine the acidity, we need strong base. If you want to determine the alkalinity, we need strong acid. So king of all chemicals, that is H2SO4, is the strong acid which we use to determine the alkalinity. This is the titrant. And there will be indicators. So there will be endpoint indicators. Endpoint indicator. There are two indicators we use here also, that is methyl orange, same indicators everywhere. Methyl orange. So the methyl orange is one indicator Another indicator is phenolphthalein. Another indicator is phenolphthalein. We use phenolphthalein as another indicator. Phenolphthalein as is another indicator. So there will be working ranges for both phenolphthalein, and there will be working range for both phenolphthalein as well as the methyl orange. There will be working ranges. So generally the phenolphthalein will work in a range of generally it is methyl orange. Methyl orange is generally the methyl orange is works in a range of 2.8 to 4.4 pH. It works in a range of 2.8 to 4.4 pH, and it works in a range of 8.3 to 10.6. 8.3 to 10.6. That means this methyl orange works in acidic medium, and this phenolphthalein works in basic medium. So generally we are having three major alkalinity causing compounds. These ranges, generally the ranges of these three varies from when the pH is around 14 to 10.2. So this OH minus alkalinity is predominant when the pH is between 14 to 10.2. And this CO3 2 minus pH, the range, this is predominant when the pH is ranging from 8.3 to 10.2. 8.3 to 10.2. So this HCO3 is predominant when the pH is ranging from 4.2 to 8.3. 4.2 to 8.3. See here, so these indicators, generally these indicators, I already told you, that turns into one color into another color. Generally it turns, actually the color of the methyl orange is orange, red or pink. Nearly it has different shades of color. So generally it can be in orange or pink or red color. So that is the basic color. For example, let us take it as pink color. So this pink color will change into the yellow color. This pink color will change into yellow color within this working range. This pink will convert into yellow color within this working range. So that means when you are doing titration, so you have started from 14. So this is alkaline water, so the pH will be high. Acidic water, the pH will be low. Alkaline water, the pH will be high. Now you have started from a higher pH, and if you add H2SO4, this pH will come down. This pH will come down. At some stage it comes up to 4.4. Until that time the methyl orange will be in orange or pink or red color. Suddenly when pH reaches to 4.4, it turns into yellow. That means it indicates that the pH has reached 4.4, and it continued to be yellow up to 2.8. Once it reaches 2.8, it surpasses 2.8, it go beyond, then it again turns into pink. That means its working range is over. So similarly, the phenolphthalein also works in a range of 8.3 to 10.6, and in this range it converts into yellow to pink. It converts into yellow to pink. So these are the working ranges and color conversions of these indicators. Now, so this is alkaline indicator, this is acidic indicator. Now I have taken a water which is alkaline. Now I am doing titration. So first of all, the indicators I have used is phenolphthalein. Now at 10.6, I can identify the pH at 10.6. So now at some location 10.6. So I have identified, because this is the range where CO3 is starting. Right? So now, so at this range at some range 10.6, I found the graph is like this. Now when you are adding the acid, see this is titrant quantity. So ml of titrant added, ml of titrant added. So this is the quantity of titrant, this is pH. This is pH. Now at 10.6 I found that the color has converted into pink. That means this range has started 10.6. And again at some range, again it has converted into yellow. That means this range is over, this working range is over. So at 8.3. So at 8.3, its working range is over. Its working range is over. Again I am adding, keep on adding the acid. Now I have added methyl orange. Now this is the titration graph at some point 4.4. At some point of 4.4, it turned into yellow. That means 4.4 has reached. That means 4.4 we have reached the point 4.4. We have reached the point 4.4. So now using these indicators, here I have used phenolphthalein, here I have used methyl orange to identify the boundaries. So in this boundary, who will exist predominantly? In this region is predominantly taken by CO3 2-, right? So this region is predominantly taken by CO3 2-, and this region is predominantly taken by whom? HCO3-. This region is predominant taken by HCO3-, because these are the ranges. And if it is beyond this, then it is taken by OH-. So where is your pH of water? Where is your pH is standing? Upon that, so the presence of anions or the presence of the alkalinity varies. Now what I will do now here is, here the indicator I am using what? Phenolphthalein, right? P, phenolphthalein. This range is for phenolphthalein. So what I will do, whatever the quantity I will get here, I take it as P. Whatever the quantity of titrant I am using for this reaction, I take it as P. Here, this is the range. So here in this range, the quantity, so total quantity up to this range, I take it as M. Okay, I take it as M. Now, what is the relationships between P and M for different conditions? What is the relationship between P and M for different conditions? That is very, very important. See, the first condition, for example, P is equal to M. If P is equal to M, listen carefully. If P is equal to M, that means there is no quantity of titrant present in this zone, right? So in this zone, if there is no titrant, then there is no HCO3. In this zone, if there is no titrant is being used, that means there is no HCO3. But that means there is no HCO3. See, one more thing I would like to add here is, when there is CO3 2-, CO3 2- will get neutralized in two stages. CO3 2- will get neutralized in two stages. First stage is, this is here, it is CO3 2-. It is getting neutralized. Here it has become HCO3-. That means CO3 2- will neutralize to half. CO3 2- will get half neutralized at this point, remaining half will get neutralized here. Remaining half will get neutralized here. If P is equal to M, if P is equal to M, that means HCO3 minus is not present. If HCO3 minus is not present, how CO3 2 minus will present? Because CO3 2 minus, if it is present, so it will get neutralized to half, 50% only here. Remaining 50 should present here. That means if CO3 2 minus is present, definitely HCO3 minus will present. If CO3 2 minus is present, definitely HCO3 minus should present. But if HCO3 is present, it is not needed to CO3 to be present, because HCO3 can be inherently present in water. Are you getting my point? So without CO3 2 minus, HCO3 may present. But when CO3 2 minus is getting neutralized, definitely it has to first become HCO3, and then this HCO3 will become H2CO3. Are you getting my point? So that is why generally when there is no titrant here, that means completely CO3 2 minus is also not there, HCO3 minus is also not there. Only thing, OH minus alkalinity is present. So only if OH minus alkalinity is present, then only you will be having only P, which is equal to M. So if P is equal to M, that means the alkalinity is caustic alkalinity. The alkalinity is caustic alkalinity. See, this is a very simple concept but little confusing concept. You need to understand it clearly. You need to understand it clearly. If P is equal to M by 2, if P is equal to M by 2, okay, see, I told you CO3 2 minus will get neutralized only half. So whatever the amount of acid needed here, the same amount of acid needed here for CO3 2 minus. For example, from here to here, CO3 2 minus needs 10 ml of H2SO4. Okay, from here to here, from this point to this point, up to these 2 points, CO3 is taking 10 ml of H2SO4. The same CO3 will take another 10 ml because only one hydrogen is taken in this range. Another hydrogen will taken in this range. So same 10 ml is required for CO3 2 minus. Same 10 ml. That means 10 plus 10, that is 20 is M. P is 10. When P is 10, M is 20. That means P is equal to M by 2. So that means only CO3 is present. When HCO3, see, there are 2 HCO3s will present in water. One is inherent. One is inherent means already HCO3 is existing in its natural form. Another HCO3 is coming from the neutralization of CO3 2 minus. Another HCO3 is coming from neutralization of CO3 2 minus. Now, when there is no inherent HCO3, then only whatever the neutralized CO3 2 minus, whatever the HCO3 which comes from the neutralization of CO3 2 minus only present in this zone. In that case only P should be equal to M by 2. Isn't it? So if 10 ml of titrant is needed for this CO3 2 minus to become HCO3 minus, the same 10 ml is needed for this HCO3 to become H2CO3. So this condition is satisfied only when the alkalinity is completely carbonate alkalinity. When the alkalinity is carbonate alkalinity, completely, here also same, completely carbonate alkalinity. Okay, carbonate alkalinity. when P is less than m by 2, P is less than m by 2, this is P, okay, and this is m. M by 2 means what? Half. That means P is less than m by 2. For example, this is m by 2, this is midway. So this is m, this is m by 2, this is P. So there is small difference here. Observe it clearly. Observe this clearly. In the path of m, so this is 0, this is m, and somewhere this is P. Obviously, P is the requirement of CO3 2 minus. Okay, P is the requirement of 50% CO3 2 minus, isn't it? So 50% CO3 2 minus will get neutralized in this range. The same amount is needed on this direction also, same amount, that is P again, or we can say this is 2P. Okay, again this is 50%, again this is another 50% of CO3. That means HCO3 to H2CO3. This part is CO3 2 minus to HCO3 minus, and this is H2CO3. And this part, there will be inherent, I told you, there will be inherent, already existing HCO3 will present. Already existing HCO3 is present. So whatever the HCO3 already existing in water will become H2CO3 here. Will become H2CO3 here. So that means when this condition is prevailing, that means there is carbonate alkalinity as well as there is bicarbonate alkalinity. Are you getting my point? So here in this case, when P is less than m by 2, when P is less than m by 2, then in that case the condition here is the alkalinity present in water is carbonate as well as bicarbonate alkalinity. So the alkalinity is carbonate alkalinity as well as bicarbonate alkalinity. Carbonate alkalinity and bicarbonate alkalinity. And next condition, P is greater than m by 2. When P is greater than m by 2, when P is greater than m by 2, so this is not m by 2 now, this is m, this is P, and somewhere here this is m by 2. That means 0, m, this is P, and this is somewhere m by 2. So P is greater than m by 2. P is greater than m by 2. See here, this is P, right? This is P. So if it is completely having CO3 2 minus, then the same P should be present on the other side, because up to P CO3 2 minus only half of the CO3 2 minus is getting neutralized. That means another P is needed. That means somewhere here I will get 2P if it is only having CO3 2 minus. But there is no titrant on the other side in the second stage, it indicates that here it is not completely CO3 2 minus. Here it is not completely CO3 2 minus. There is some amount of other alkalinity, because up to this point this is m by 2. So m by 2 into 2, that is m. So this part is only CO3 2 minus. This part is only CO3 2 minus. There is another half. There is another point is there, that is, so that is OH minus alkalinity. That is OH minus alkalinity here. So if this is m by 2, so we need another m by 2 here, that is 2m. That means m. So this portion, whatever the portion is there, that is taken by whom? So OH minus. This is OH minus alkalinity. This is OH minus alkalinity. That means when P is greater than m by 2, we will be having both carbonate. The alkalinity is carbonate and caustic. The alkalinity is carbonate and caustic alkalinity. Carbonate and caustic alkalinity. When P is equal to 0. When P is equal to 0. If P is equal to 0. So that means completely crush this. Completely 0 this is. We have started our graph. See. So if this is the axis. If this is the axis, forget about this part. So don't look at this part. Only look from here. So P is 0. P is 0. Only this part is existing. That means what? Only HCO3 minus inherent. Because when there is CO3 2 minus, there will be HCO3 minus. But if HCO3 minus is present, it does not mean that there will be CO3 minus. I have told you already. If CO3 minus is present, then HCO3 should present. But if HCO3 is present, it does not mean that there will be CO3 2 minus. Are you getting what I am saying? So this is only inherent HCO3. Inherent HCO3. Okay. The alkalinity is bicarbonate alkalinity. So this is what we need to understand from the titration. Very, very important for the examinations. Very, very important for the examinations. What I will do now, I will prepare a table format of this, and so that you can easily revise. So that you can easily revise the topics which you have discussed. Different conditions and what is the concentration of OH minus, what is the concentration of HCO3 minus, CO3 minus, 2 minus, all these things we will prepare in a form of a table for different conditions. So relation between P and M and the concentration of OH minus, concentration of CO3 2 minus and the concentration of HCO3 minus for different conditions. The first condition, when P is equal to M. When P is equal to M, then OH minus concentration is M, OH minus concentration is M, and CO3 2 minus is 0, HCO3 minus alkalinity is 0. When P is greater than M by 2, when P is greater than M by 2, when P is greater than M by 2, then OH minus is 2P minus M. It is equal to 2P minus M. It is equal to 2P minus M, and CO3 2 minus is 2 into m minus p. 2 into m minus p. 2 into m minus p. See, these things we can correlate easily with the concept which I have explained you already. So you go back to the concept and correlate these formulas. So I will explain for one thing. So for this thing I will explain. I told you. So this is 0. So p is greater than m by 2. So this is m. This is m. So this is m by 2. So this is p. So p is greater than m by 2. I told you this part is what? CO3 2 minus. So the same part on this side. So this is again CO3 2 minus, because I told you how much of H plus is needed up to this point, that much is needed on this side also. Okay, so this is the dosage. So this is the dosage of CO3 2 minus. This is the dosage of CO3 2 minus. Similarly, CO3 2 minus to HCO3, and here HCO3 to H2CO3. So this one we know, m minus p. M minus p is the dosage needed to convert HCO3 to H2CO3. That HCO3 is also coming from CO3 2 minus. That HCO3 is coming from CO3 2 minus only. And this gap is of what? This gap is OH minus alkalinity. This gap is OH minus alkalinity. So here, so this concentration, I want this one only. So this is m minus p. This is m minus p. The same m minus p is needed on this side, isn't it? So this is 50%, another 50% is needed here. So m minus p and m minus p. 2 into m minus p. This is CO3 2 minus. M minus p, the same m minus p this side. 2 into m minus p is the concentration of CO3 2 minus. So total this is m. Total this is m. M minus this one. M is the total. In this is CO3 2 minus. So m minus this. That means what? M minus 2 into m minus p, which is nothing but, so this will become 2p minus m. So this is OH minus. This is OH minus alkalinity. Are you getting what I am saying? So whatever the concepts which we have discussed, using those concepts we can easily frame these formulas. We can easily frame these formulas. Okay. So now this is 0 now. If p is less than m by 2. If p is less than m by 2, then this is equal to 0, and this is 2p, and this is m minus 2p. M minus 2p. M minus 2p. So next is p is equal to m by 2. P is equal to m by 2. Then p is equal to m by 2, then it is completely carbonate alkalinity. It is 0. This is 2p or simply m. And this is also 0. Okay. When p is equal to 0, then completely it is bicarbonate alkalinity. Okay. When p is equal to 0, so it is completely bicarbonate alkalinity. So these are the different values of alkalinity for different conditions of p and m, or different relationships between p and m. Okay. So this is about alkalinity, and as per IS 10500:2012 code, so the range of alkalinity, acceptable limit is, it should not be greater than 200 mg per liter in ideal conditions, and it is relaxed up to 400. It is relaxed up to 400 mg per liter under unavoidable conditions. When there is no ideal source is present, then it is relaxed up to 400 mg per liter. And what is the problem when the water is alkaline? What is the problem when the water is alkaline, and what is the problem when the water is when the pH acidic, and all we will discuss in the next class. Okay, thank you so much. Thank you.